So, I designed this thumbnail to kind of attack your insecurity about your own understanding of the world and kind of, saying I have some secret knowledge, right? And I feel like this is the exact angle to take, right? With like all these masses, and then like, you see this kind of mysterious thing looking up here, right? Um, we have to lean into the idea that and really truthfully, this is something that needs to get said, which is that rigorous mathematics and physics is the only occult knowledge of our time. Okay, the rest is garbage. The rest is utter nonsense because these masses, right, they're all on their phones that are distracted by surface level noise like politics, AI hype, conspiracy theories, whatever. The true possessors of true power, right, they are operating on a completely different game entirely. And it's not even a game. It's like something that transcends a game. And it is built on category theory, stochastic analysis, invariance, like these really important ideas that humanity has had the ability to come up with. Okay, so you don't have to stick around for the video, but honestly, I'm really only focusing this on to like a 1% of the population, maybe less, even 1% of the physics and math population. The rest, everybody is stuck up at base camp, if you will, of Mount Everest. Okay, because most of the scientific world is hallucinating right now, and they're suffering with something called AI psychosis, which we're building these massive computational powers. These computational towers, right, on these swampy kind of foundations, and we're treating neural networks as these magic black boxes because the guys upstairs that are in charge of Google DeepMind or anti-gravity or whatever, they lack the geometry. They lack the mathematical skill. They lack the skill of proof to understand, an energy loss landscape, right, which is just energy minimization or optimality. They lack the stochastic calculus to understand the diffusion and the geometry itself. So again, and I see people on Twitter that are talking about like, oh yeah, manifold is just a way for these physics and math people to their words that they throw around to just like sound better. And it's like, well, some of them actually that's true. Okay, and that's their AI psychosis. Okay, the academic industry is designed to keep you at base camp. In other words, it's encouraging you to specialize early, to publish incremental papers, and then farm your H index without ever understanding Mount Everest. Okay, you're just chilling kind of at the summit, right? You're a tourist that's taking selfies at the ticket booth to climb Mount Everest. Okay, we are not tourists, and I'm going to show you really what it looks like at the summit, all right, and give you just a taste, okay? Because you can imagine all of these peaks as like spores, if you will, of enumerative geometry or of the monster group that's describing all of math and physics and everything's contingent upon it, right? We're not going to be tourists. We're going to climb it, and I'm going to try to make something that will help you break the 4-minute mile. And we're going to unify physics, math, philosophy, all of that into a piercing kind of gaze, which is that the curriculum itself is going to be designed not to be hard, all right? It's not going to be hard just for the sake of being hard, all right? The curriculum that I'm about to show you is the minimum requirement to function as a sovereign intellectual in the 21st century. Otherwise, you're going to be dependent on an abstraction of an abstract understanding of everything, and you're going to be learning all of these equations or applying all of these things and having no idea how they work. And the AI is going to essentially be thinking for you. Okay, so this is essentially the plan that I have. I was just basing it off of the camps and the destinations that people use when they hike Mount Everest, which is you need to get to the base camp, then you need to get to Camp 1, Camp 2, Camp 3, Camp 4, and then kind of there's like a death zone, around this area. But, people who make it to the top can see for sure. The death zone is not really like, too much, the government's going to kill you or whatever. No. The death zone is more so like a it's like a people give up right here, or people don't go further enough, so then they just kind of like stop here, and then they just stop at camp for the rest of their lives. Right? So nothing's wrong with that. You're just not going to be part of the percentage of people that make it to the top and that are surveying, the true nature of physics and mathematics. Okay, and you're not going to be able to handle computational science. We're not going to be able to really think about them in a way that is complete. You have an incomplete understanding of everything, and that hence makes you stupid. Okay? That's truthfully, if you have an incomplete understanding of how the world works, of how physics and mathematics rigorously establishes the theory of what we have, it makes you a drone, and it makes you one of these guys. Okay? I'm sorry that might trigger some people, but that's just the truth. So the climb, and I'm not trying to sound like some Andrew Tate type figure or whatever. I'm just telling you, this is what's happening. This is why, and this is dangerous, because there are people who are genuinely getting AI psychosis. Okay, because they don't even know how to logic. They don't even know how to prove anything. All right, they can't tell if the AI is giving a correct proof or not, and hence they're trying to, prove Navier-Stokes with AI. Right. And it's like, and these are like guys that are really, and most of them don't have mathematical skill. Okay. Most of these guys are clowns with researcher, I'm an AI researcher or whatever. And they like tune hyperparameters that they don't understand the energy landscape of. Okay. So the client, we need a strategy. Okay. We need a protocol to help us get from point A to point B to point, whatever. Right. And the protocol is this: read it and prove everything within that book. All right. And compute everything, work every problem, create problems out of those books in a creative way. And you need to be able to play with those creative ideas intuitively. And then again, each camp here is going to have foundational texts that are going to be mastered before you get there. Okay. To say that you're at camp 1, you have to have had finished some texts. And then also with those ideas, you need to map the contingency of those ideas. How does logic, or how does set theory, or how does Lever's theory of the category of sets, how does this relate to flat ontology? Or how does this relate to metaphysics? Or how does this relate to epistemology? How do I know something? Right? These are very important questions that you need to revisit all the time and find a community to talk about these things with. Right? Topos theory, type theory. These are very important layers that are contingent upon philosophy. Okay, and that's not the primary goal here, but you need this philosophy and thinking. The whole shut up and calculate thing is means of abstracting something from having a true, deep, critical lens of the ontology of our physics. Right, what is actually being observed? What are the objects that are being concerned when we measure something? Right. Fun fact. Quantum mechanics really doesn't have a true ontology of physical reality. And a lot of people are saying, well, that's not science's concern, right? We don't care about physical reality. Okay, well then, what is it, physics then? Okay, anyways, that's a rant, but be able to also learn programming skills. If you need to start with vibe code, okay, but get a rigorous understanding of the machine from the ground up, okay? And learn how to compute things with machines, okay? And that's something we're going to get into in this channel as well. But I just kind of want to show you, this is the strategy, okay? This is the strategy on how to handle what I'm going to throw at you. So the base camp should take about 1 to 1.5 months if you lock in, all right? Again, this is a theoretical way to break the 4-minute mile, to climb Mount Everest. Stop thinking in English. This book, Cunningham's Logical Introduction to Proof, is going to help you to stop thinking in English and start thinking in logical structures and truth values and unambiguity, right? The filter, what this filters out here, most will really quit around, logical introduction to proof or sets for mathematics, because they refuse to be humble enough to relearn how to count, okay? So this is your syntax here. And this will ingrain everything from set theory, and you will learn how to write proofs without, and you will write proofs not to pass a class in this book, because this book is meant to be like a reference. If you read the description, it's not meant for a single class, right? It's exactly from ex nihilo what you need to get the competency of writing a formal proof by contraposition without sweating. Okay, or talking about mathematical induction, or proof by contradiction. Everything's in here. All right, the logic and epistemology for some sets, and you'll understand that sets themselves are axioms, and they're not bags of marbles. All right, so that's something you also will be able to arrive at, and this should lead into Lauver's motivation, and Roseberg's Lauver and Roseberg's synthesis of the category of sets. Okay, and this is ontology. Okay, every philosopher, every metaphysician should read sets from mathematics, because you're going to start seeing then things as mappings, and you will realize that 1 + 1 is equal to 2. And this is a statement about coproducts in a category, which and it also talks about topos theory, which is contingent upon Hegel's science of logic. All right, and he mentions this as well. This is the mathematical philosopher. Okay, so I highly recommend this book. Okay, and it should take about 1 to 2 months if you lock in. All right. Now here's the second camp. The first camp. Before getting to the first camp and saying you are at the first camp, you need to have read both of these. Why? Is because you need to harden your mind. Mathematical maturity is the ability to handle infinite complexity without losing the precision of the previous logic and proof schemes that we learned. Okay. Papa Rudin, and I know I might make a bunch of mathematicians roll their eyes like, really? You're going straight from here to here? And yes, cope with it. Well, not as a jerk, like cope with it, but like, find a way to build up to this if you don't have, again, you should probably work everything in here and realize that this also has an introduction to analysis itself and calculus and everything. This is the books that I'm providing here instantiate each other, right? But if you need to find some way to cope with it by finding an easier book first to ease you into, or even Baby Rudin, Baby Rudin and Papa Rudin, to get rid of, to get used to a style, all right? But you need to understand after this book that integration is a linear functional, and that you can define a measure space without flinching, and this will definitely get you to be able to do that. And this book is the gatekeeper because it filters out the weak. All right, it filters out the weak before you climb Mount Everest. And again, I'm putting 2 months because if you lock in, theoretically, you could complete both of these books. And again, you don't fear infinity anymore after this book. Probability with martingales is kind of this is a nexus, because we're going to take Rudin's idea of a static measure and time, and or filtration of the static measure, and we're going to be able to understand that information itself and the updating of information and our expectation about information is defined by something called a Borel-Sigma algebra, okay, or just sigma algebra in general. And you can prove this with the martingale convergence theorem. And congratulations, once you make it through all of these, you are more mathematically literate than 90% of all data scientists, okay? But you're still flat. Okay, you're mathematically literate, but you're still working in a flat world. Okay, here comes where mathematical maturity starts to be necessitated. All right, so the goal here is structure and symmetry, and that's essentially, we're going to go through algebra, categories, and linear algebra. All right, the reason I chose linear algebra, Georgy Shilov's linear algebra, is because it's meant to be an undergraduate text for physics and mathematics combined. Okay, so either one of them. This is just kind of like this is linear algebra done right, but like done better. Okay, it starts with determinants. Determinants are the first thing, and this instantiates linear spaces, which will then instantiate the idea of canonical forms. the core thing that you should be able to get out of this engine room of a book is the ability to compute Jordan normal forms by hand. And you should understand that a matrix is just a shadow of an operator. This does a really good job of doing that. Soviet mathematics books are usually very dense, very scary, but so worth it. Okay, some of the best problems to work out in this book for linear algebra. It also briefly it introduces Hilbert spaces, tensors, or whatever, but that's not the focus of this book. Okay, the focus is determinists, linear spaces, and canonical forms. And then Lang. Lang is going to show you Lang's algebra. It's like an abstract algebra book, but he just calls it algebra. Okay? That's why I like it. Groups, then go to modules, and then go to tensor products. So as you can see, it's algebra, but like, those are physics subjects, okay? And you're going to understand after this book that a vector space is just a module over a field, and you will master the isomorphism theorem, okay? Or isomorphism theorems, okay? There's several of them, but yeah. And then what you're going to do is you're going to try to establish more of a satellite view of what we have of everything so far by connecting Lever's ideas to categories. And with Lever's ideas, we're going to show that Shilov and Lang are talking about the exact same things. Adjunctions and limits. Okay, so that's what category theory allows you to do. You are now prepared for talking about taking linear algebra and taking algebra itself and curving it. This is where we have general relativity, and general relativity lives in Camp 3. All right, and again, we're going to start with Warner, and the most important when I chose this. I like it because it introduces manifolds first, and then goes into tensor forms for more of a better differential forms approach, and then talks about integration and Stokes theorem, and the exterior derivatives as well are introduced here, and I think it's a great kind of in-depth treatment of exterior differentiation. If you square the operator equal to 0, why that is, you get all of your identities that you would otherwise see in a Griffith's textbook on the front cover and have to memorize it. You can just reproduce it from differential calculus, right? And you'll also understand Stokes theorem from this book, as well as the fundamental theorem of physics. Okay, Stokes theorem is the fundamental theorem of physics. All right, and I don't think he explicitly says that in here, but I mean it's the writing is very good. And then next, you'll have the differential geometry and symmetric spaces. This is Lie algebras and root systems. You'll essentially be able to know the root systems and understand that the standard model of physics, of particle physics, is just a specific geometric shape. And this is why I think, Helgeson's book is a very good supplement to this particular and by the way, as we continue to go up after this, the order in which you do these books matters less and less and less. Okay, the order in which we do these books, it really doesn't matter. If you want more linear algebra, do this one first and then go here and then go here. Actually, I would say you need to do this one before this one. Okay, but before you talk about root systems or whatever. But what this book will do for you is it's going to link algebra to geometry. Okay, it's going to link algebra to geometry itself. That's what I like about this book. And we will do this with something called symplectic spaces. And the reason why this is important, and again, this will also review drill in linear algebra, but talk about symplectic spaces as well. And depending on which way you want to go, I think definitely going this sequence that I recommend is essential. Okay, but that's the core competency that you should be able to have after all three of these books, which is exterior differentiation, Stokes theorem, root systems, and symplectic spaces. Okay, this is probably the hardest part. Okay, it's applying everything. This is the functional cathedral, and I kind of think this is still Camp 4-ish, almost to the summit. Um, but what happens? This is more applied. All right. And I would recommend following my differential equation series, but I reference these books all the time. Okay. This is the functional cathedral. And the reason I call it that, and this is the hardest claim because you're doing infinite dimensional engineering. And this, I guess the core competency you would be able to get out of these books here is weak derivatives, spectral decomposition from functional analysis, being able to apply, Lie groups to solve differential equations and, vector fields that, encode, symmetries and, symmetry generators. And then also, Arnold just treats differential equations in a very applied way and in a physics way. So again, and I would say the time on this one depends on how serious. I would say this is really the time that's ripe to really seriously learn programming. Okay, programming is just it. It comes very naturally when you study differential equations. Okay, and especially when we're talking about applications of differential equations. Now let's look at the advanced base camp here. I would recommend Arnold's Classical Mechanics. You're gonna stop writing. You should probably never write F equals ma. You should just derive it. I think. You'll never write F equals ma ever again. You'll never think about forces in that way, and you're just gonna write symplectic manifolds and Hamiltonian systems. Okay, that's physics. That's real physics, right? Rest of physics is kind of fake because it depends on coordinates. And the competency of this, you should actually be able to derive conservation laws from Poincare invariance. Okay? And then I think after reading this one, you can, it's a little fuzzier. And also you can study electrodynamics or classical field theories a little more if you think it's interesting. You can start Penrose's Road to Reality. I would say you're at a good point in understanding Penrose's Road to Reality a little bit. But yeah, I mean, there's a lot more leeway for this. But then next, I would recommend Riemann surfaces. Understanding complex geometry that's required for string theory is really important in Donaldson, or in Donaldson's book on Riemann surfaces. Talks about genus and these the very important role that complex numbers play in topology and encoding these very special holomorphic type surfaces. Okay, and then this will allow you to go in a deep dive on Atiyah. Okay, you can start reading Atiyah after this, I would say. And this will talk about the Yang-Mills functional, and you will see from this that forces are curvatures on a bundle. And I would read the original writing from 1979 itself. And it's because it's just very elegantly described. It depends on a structure group, which we are encoding onto a principal bundle, and that principal bundle will then instantiate the forces and the curvature and the gauge fields that give you forces. And their curvature on a principal bundle, not on space-time or whatever, okay? So that's really important. This is giving us Yang-Mills fields and Yang-Mills theory. Costello renormalization is the next step because you're going to be able to solve divergence of, using Borel transformations and, solving the infinity problem in quantum field theory, essentially, using something called heat kernel regularization. That's probably the most important thing. Ultraviolet, infrared, fixed points of theories, renormalization, everything is in here. Okay, love this book. I think it's like 200 pages long. By the way, guys, most of these books are like 200 pages long. All right, most of them. This is probably the only one that's like maybe 400 pages long, but most of them are pretty short. Okay. Oh yeah, and Lang. Right, that's kind of long. But lastly, we get to the death zone. And I would say the death zone is kind of like, like probably right here. All right, because you're losing oxygen. I mean, I technically said this was camp 4 here, but you would have to have this completed, and I think this is advanced. The death zone is clearly somewhere here where you're at the summit and you might die, okay? Or just quit. Well, I mean, you're probably too far deep to quit, but you'd probably quit on your aspiration of getting to the summit. In other words, that's what I mean. This is where people's dreams die, all right? Not really deep dreams. It's not really like, your physics, like, becomes shit because you didn't make it to the top. Like the climb and the journey itself, you're growing, right? You're becoming capable, right? But then your dream dies, probably around these areas. I'm just kidding. It won't, because this stuff is so interesting, guys. So Watanabe and Ikeda will talk about stochastic integrals, and you'll understand that stochastic integrals are actually flows on manifolds. And you can do calculus then on fractal paths and understand the Malyavin calculus, which is integration by parts on a path slice. And it codes a curvature of a probability space. Okay, I sound like I'm kind of like going off on a tangent, but stochastic differential equations and diffusion processes. And it relates back to probability with martingales, but it also incorporates the renormalization and effective field theory. So this is why it's so high up. Like, and this is what also kinetic theory relies on, is stochastic differential equations and stochastic flows on manifolds. All right, that's what kinetic theory is. There's also Harrier's important paper in 2014, which shows us an introduction, or this he didn't discover in 2016, but 2014, but the regularity structures that are embedded from the renormalization of 5 to the 4 theories, which is covered in Costello's book, allows you to multiply distributions. So this allows you to describe space-time, stochastic partial differential equations. And it's kind of meaningless, right? Like, what do you mean to multiply 2 distributions together? Well, regularity structures allow you to solve this nonlinear stochastic PDE, all right? And then lastly, by a renormalization noise term, okay, or Gaussian white noise term. Lastly, this is a paper, I think. You can find it. It's not hard to find. I think it's on the archive. Lastly is the exterior derivative, the exterior differential systems with Euler-Lagrange and partial differential equations. This is by Bryant, Griffiths, and Grossman. Probably one of the best books out there in the world, which it talks about Poincaré Cartan forms and conservation laws. And you should be able to get out of this book to be able to treat PDEs. Differential equations themselves were never fundamental. Okay, you're never trying to solve a differential equation of reality. All right, and I just think like that's one of the most beautiful things about physics, is because we have this idea that we can write down and determine the exact future of everything. But it's like, well, actually, that thing that we wrote down depends on a beautiful kind of algebraic ideal in an exterior algebra. So it's like, nah, never mind, you're wrong, and it belongs to a jet space. All right, so very cool stuff. Again, I would also think at the death zone you should read the original Hormander Fourier operators. This then is a prerequisite. All of this is probably a prerequisite for really being part of the percentage of people that actually add value to machine learning. Okay, in like a real kind of like tangible progressing humanities understanding of machine learning. All of this is probably what you need as prerequisite, and also understanding the theory of Fourier operators themselves. In terms of D modules and algebraic methods of solving differential equations. Okay, but I would read through those sheaves and algebraic geometry of Kashiwara. I spelled that wrong. But D modules and holonomics as well. And Ekale's resurgence and alien calculus papers are super important. Okay. So this would probably take around, again, it'd probably take around 3 to 5 months. This is the longest death zone, I would say. But the summit, if you make it to the summit, the goal here for making it to the summit of all of what we understand about physics is, in theory, the Langlands program, getting the language of string theory, and um, the understanding really deeply that that number or number theory, shape, and physics are all unified in this really weird, beautiful, and terrifying way. um, that keeps people up at night, like legit. It's just, I mean, and it's not like the summit is something that's like incredibly gonna make you have your own psychosis. Like it's like, okay, well, do I get AI psychosis with the rest of the population, or do I get number theory, string theory, K theory, M theory psychosis? It's like that's not how it is at all. The logic is so deep and it's so beautiful, and at the top, it's just like, man, it looks exactly like this is exactly the feeling that it looks like. Um, or the feeling that it invokes. So up here, you know that you've mastered, or I'll talk about the books first. So um, I think the most important thing to get out of algebraic topology as a subject is embedded in here. Singular homology, characteristic classes, and cobordisms. You should classify holes in reality, right? And you can do that with cobordisms as the classification of manifolds. K theory, you should be able to, you have like vector bundles, and you can describe bot periodicity. Again, check my differential equations video. I talk a little bit about K theory and instantons and all that stuff. Again, K theory is a physics theory, man. Okay, it's physics, and you'll realize that vacuums have stable periodic structures, which it comes off as mathematical, but it's really not. Okay. Vertex operator algebras. You'll what this relates affine Lie algebras to the Moonshine module itself, and you will see that the monster group itself is, and its spores are lurking inside of string theory. So the monster sees string theory, in other words. Okay. And the last thing to talk about is the quintic threefold from to quantum cohomology and algebraic geometry and mirror symmetry. Okay. And the competency that you would get out of this is to bridge something that's called the symplectic A model with the complex B model worlds. And you'll be able to compute Gromov-Witten invariance after this. All right. What will happen at the summit is you will then be able to understand InLab. Which is the joke I have here, right? Like, oh god, we've climbed Mount Everest here. The InLab is right there. Okay, that's the joke. But InLab is notoriously kind of like hard to understand for normal people. Who it's not really normal people, it's just people who haven't climbed the Mount Everest, and I guess that isn't really normal people. But also you appreciate in theory, whether it's physical or not. It's a beautiful piece of art that you can respect and enjoy, and show like that it's deeply ingrained into the enumerative geometry of the universe. Okay, in the way that the universe structures itself. Also, hypothesis H excites you as well. All right. So, and hypothesis H no longer is a buzzword to you. It's a research program, and you now have the tools really to navigate essentially the jet space of reality. And you're ready at the summit. You're ready to create and not just consume, material. All right. And that's essentially the goal, is to understand that math is within us. Physics is, the geometry of the vacuum itself. Geometry is the algebra of symmetry. And, I kind of go on a rant here, but, algebra is the logic of structure itself. So, you're no longer a tourist here at the summit. You have prolonged the infinite spaces within you, and you understand these things very deeply. Okay? Thanks for sticking around. Let me know what you guys would like to see. Obviously, I have all of these books. I've skimmed pretty much most of them. I haven't this is something that I've come up with that I think would really help. I guess the next, this is I've skimmed through all of these books. I haven't worked every single problem in them, but I spent a lot of time thinking about physics ever since I got out of high school. I'm graduating soon, and I realized that I need to go back and all of the things that I've skimmed, like I need to get it into a nice cohesive picture, um, to prepare myself for grad school. And I'm thinking even this should be something that I should be able to put out there on the internet, and people should be able to see this and find value in it, and appreciate it, appreciate the mountain for its scenic, view, but also feel the urge or the itch to say, hey, I want to climb it. How do I do it? um, this is the roughest picture that I could make on how you could do it. All right, thanks for watching. Peace out.